This is section 6.1. We're going to introduce area. So we're going to approximate an area, generally under a curve, and find the area under the graph of a function. So we're not going to find the exact area today, but we are going to approximate it. So the first question is, how do you find the area of a non-traditional shape? And what I often do to start this set of notes is talk about the shapes that we do know. You know that you have a formula for a circle. You have a formula for a square and also for a rectangle. You have a formula for a triangle. And then we can get really fancy. You actually have formulas for a parallelogram. You might not remember it. There exist formulas for a trapezoid. You can get into your regular polygons. All of these have area formulas that we discussed back in geometry. But what happens when it's an unusual shape or an irregular shape, non-traditional shape? And so what we're getting at is the area under the curve. So here's my function, y equals f of x, and we're slicing it into rectangles. So we've got 3, 4, 5 rectangles. So what we can do is find the area of each rectangle, add those together, and that gives us the area underneath the curve. Now, they've broken this down into saying the area is the width times the height. That's for a rectangle, we know that. But the way that we're going to get that width is from B minus A. A is your starting place for the area, and B is the ending place for the area. If I take all of these heights and kind of average them out, it winds up to be this. So I don't love this picture, but the area of all 5 rectangles on the top is the same as the one area on the bottom. So our definition, area A under the graph of a function from A to B. Suppose a function f is non-negative and continuous on a closed interval from A to B. Partition A to B into n subintervals, I just mean rectangles, from x sub 0 to x sub 1, x sub 1 to x sub 2, etc., of each width. And this is our delta x. So our formula for delta x is b minus a over n. Just remember that this is the width. That's all it means, that change in x. In each subinterval, let f of c equal the absolute minimum value of f on each subinterval. These form the lower sums. This notation looks so crazy, and it jumps right into it, which I don't love. But basically, this delta x is your width. This becomes the height. F of x, f of a specific value, that's your height. And so what this really is, and again, it looks crazy, but don't panic. Here's your height times your width. Here's your height times your width. So however many partitions or rectangles you have, it's really here's your height times the width. We'll do another problem like that in a few minutes. The idea is 5 rectangles will approximate the area, but the more rectangles you have, the better the approximation is. And so at the bottom of the page, this is why we're going to infinity. If you have an infinite number of rectangles, that will give you the exact area under the curve. So this first page introduces the idea and goes really deep, really fast. Summation notation. I'm going to introduce this to you because I don't think you've seen it before in your other math classes. You may have seen it in Excel or Google Sheets. That big, this guy's called a sigma, this is a Greek letter. Stands for the sum or the summation, where you add things up. So down here is my start. Up here on the top, this is my stop. And then this is the term, whatever it is. So this particular example is kind of tough because it's all letters. I, M, J, N. Not so helpful. But if I come down here to example 1, this one's a little bit easier. So remember, this is the start. Up here's the stop. And then I squared plus I, that's what we substitute into. So what do I mean by that? This 3 goes in, and then with summations, you always count up by 1. There are no other options. So we'll use I equals 1, I equals, not 1, excuse me, I equals 3, I equals 4, I equals 5, and we will substitute each of those into this expression. So this becomes 3 squared plus 3, 4 squared plus 4, 5 squared plus 5. So then we'll go through and figure out what this is. So I've got 9 plus 3, which is 12, 16 plus 4, which is 20, and 25 plus 5 is 30. So 50, 62. So it's another way to write adding, or that sum of something. Does it feel a little bit more complicated than just adding up those pieces right now? Yeah, it does, but it does come in useful later. And don't totally ignore this idea. This sigma notation is all of unit 10, the whole thing. So we're just going to get started with it now, but when we get to unit 10, it's everything. Now, I find this statement debatable, but we'll go with it. It is convenient, I'm not sure about that. It is convenient to write sums when adding up rectangles under a curve. So instead of writing out every single individual rectangle, they're suggesting that, hey, we can use the summation notation to write a formula to add up all the areas of all the rectangles that approximate the area under a curve. We have two versions for this. R sub n, this means right. We haven't really talked about right versus left, and L means left. I don't have a picture for you right away, unfortunately. So here's a curve. If I break it into rectangles underneath, right-hand rectangles use the right-hand corner to determine the height of each one. So they look like that. If I do this again, 1, 2, 3, 4. Let's do it this way. If I choose L, left-hand rectangles, it's the left-hand side that determines the height. So my first function was increasing, my rectangles were too tall. My second function was decreasing, the rectangles were still too tall. But some will be too tall, some will be too short, depending if it's increasing or decreasing. Right now, I just need you to know, all right, left and right look a little bit different. So example 2, we want to calculate R6 for f of x equals x to the -1 on the interval from 2 to 4. So we need to take these pieces and fill them into this formula. So now I've got R. So let's fill in the pieces here. So R sub n is equal to delta x summation j equals 1 to n f of a plus j delta x. So let's come over here on the side and figure out what's what, because there's a whole lot going on here. Let's start with delta x. Remember, delta x is the width of each rectangle, and they're going to be the same width. So this would be b minus a divided by n. B is the ending value. This is a, this is b. So it would be 4 minus 2 divided by the number of rectangles that we have, and that's the little subscript here. This is n. So 4 minus 2 is 2 over 6. This becomes 1/3. So delta x is 1/3. The other thing we need, okay, up here's n. N is equal to 6. A is the starting value, which is 2. J, you're not going to put a number in for J. J counts every time you go through the cycle or the loop. J gets one more onto it. So that's not anything that you have to change. We just know where J starts. We know where J ends, and it goes up by 1 each time. So when we fill in our formula, I have R sub 6. Delta x is going to be 1/3. Here's my sigma notation. J equals 1. N we know is 6. F of a plus j delta x, that's really just f of x, but a little extra stuff in it. So this is f of 2. Remember, j stays as j, and delta x is 1/3. All right. So this piece, this f of x stuff, f of 2 plus j, 1/3. All of that has to get substituted into our function. And our function is this x to the -1. So what do I mean by all of that? I mean that often if I have f of x equals x to the -1, and I said, all right, find f of 3, you would have no issues with this. You'd tell me, all right, it's 3 to the -1. So we're doing the same thing. This time we're just substituting in 2 plus j and 1/3. So when we go to plug that in, this will be 2 plus j times 1/3 to the -1 power. We don't need f anymore because we've put it into the function. Here's my sigma, and here's a 1/3. So I know this looks kind of crazy. This is why where it says it is convenient, I disagree. I think to do this without the sigma notation would be a little bit quicker. But then what you would do is calculate each sum and then add them all together. So what I'm going to do is leave the 1/3 in the front. This would be 2 plus j 1/3 to the -1. I'm going to write this out so you can see what it looks like, and then I'm just going to tell you the answer. We're going to have 6 rectangles. Plus 2 plus j to the 1/3 -1. This is not the best way to write it, but I want to show you what happens with that j. And I'm sure some of you can write it right from the beginning, but 1, 2, 3, 4, 5. Okay, I left all the g's the same on purpose. So again, the sigma notation, we start at 1, we go to 6. So the first j is really a 1. The second j is really a 2. The third j is really a 3. This is a 4. This is a 5. And this is a 6. So we have our 6 rectangles. And what you can do is go through and figure out what each of those are. This first one is 2 plus 1/3. So I know that that is 7/3. It's to the -1 power. So this is really a 3/7. And this 1/3 still in the front. The next one would be 2/3, 2 plus 2/3. 8/3 flipped over. This is 3/8. The next one, those would cancel out. This is just 3. But flipped over, this is a 1/3, which makes sense because if I follow the pattern, this would look like 3/9. The fourth one I'm down here, 4/3 plus 2, which is really 6/3. So this is 10/3. Flip it over, is 3/10. 5/3 plus 6/3 is 11/3. Flip it over, this is 3/11. 6/3 is really 2. 2 plus 2 is 4, but I gotta flip it over. This is 1/4. Okay. Then I have this 1/3 in the front. Everything gets multiplied through. I don't have a calculator in front of me, so I'm going to reference the book. Guess what? This one's not in the book. So after all that, if I take 1/3 and distribute it all the way through, you're going to wind up with this quantity, 1/7 plus 1/8. This would be a 1/9 plus 1/10 plus 1/11 plus 1/12. So if you added all those up, that would be the answer to example 2. So like I said, I disagree with the statement that it's convenient. I don't think it's convenient at all, but it is something I need to introduce you to. So for power sums, that whole process was kind of ridiculous to go through and evaluate each one individually. So there are known quantities, known functions that have an answer already. So instead of me having to go through and say, all right, 1 plus 2 plus 3, it can be this form for the formula or this. These would simplify to be the same thing. This version or this version. Or this version or this version. So basically, if you took the version on the right and did some common denominators and factoring, you'd get this version on the left. You can take the version on the left. You're going to love this. You can turn it into partial fraction decomposition, I think. I think it'll work kind of upside down. Regardless, these two things are equivalent. So depending on what you're doing, maybe the version on the left or the version on the right. It does say we're expected to memorize these. I don't expect you to have them memorized like first thing. But once we get deeper into this BC stuff, this is a topic that has to be memorized. All right, so for example 3, I'm going to show you how to do this kind of 2 ways. There's the way that if you get totally stuck, at least it's something. This would be j squared. We're going to start at 1 and end at 6. So this is 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared, and whatever that turns out to be. If I jump into the formulas and look at j squared, this would be, I'm going to take the first one. This would be n, and n is that number on the top. So this would be 6 times 6 plus 1 times 6 plus 2 all over 6. So if I look at this, that's just a coincidence, by the way, that the 6 in the front and the 6 on the bottom are the same. Total coincidence. But conveniently, those would cancel out. So 6 plus 1 is 7. 6 plus 2 is 8. 7 times 8 is 56. All right, that took me a little while, but I found it. I have a typo in my formula. One of these days, I will get all of those typos figured out and corrected, but today is not that day. So up here, this expression should really be 2n plus 1. So that's my mistake. So this should be 2 times n plus 1. 2 times 6 is 12. 12 plus 1 is 13. So let's clean this up a little bit. This is going to be 7 times 13. The 6's do still cancel out. So if I come up here, 13 times 7, I get 21 to 91. And while the camera was off, I did go through and just add them up. And I also got 91, and the book says 91. So that summation is a 91. So yes, we should have those memorized. Yes, they should be the correct formulas, not the incorrect ones that I typed. But in terms of memorization, that's lower down on my list. I need you to know your derivatives inside out. I need you to know your antiderivatives inside out and some algebra things. If you get to these power rules, that's awesome. But if you don't, they are not the top priority. Okay, all that. So because we need more rectangles than just 6 to get a more accurate area under the curve, we're going to look at the limit as n approaches infinity. You thought those limits were going to go away, but they keep coming back. So all these mean is the number of rectangles starts to approach infinity. It becomes a really, really, really large number. So example 4, calculate the area under f of x between 0 and 4. So f of x equals x. So what is that? It's a line. It has a slope of 1 and a y-intercept of 0. And we want to find the area under the curve between 0 and 4. So over here is 0, over here is 4. So the area that we're looking at is all this. And this makes a shape that we're familiar with. This makes a triangle. So using geometry, we want to use that geometry formula where area is 1/2 base times height. I know that this is 4 units wide. If I put 4 into the formula up here, this is the ordered pair 4, 4. So the base is 4 and the height is 4. So 16, half of 16 is 8. So the area is 8. You don't have to worry about units. You don't have to tell me it's feet squared, meter squared, units squared. We don't care. We just go for the 8. Now, by r sub n, So r sub n, this is going to be the limit as n approaches infinity of r sub n. So the limit as n approaches infinity. Now, in place of r sub n, we're going to come back up here and use this formula. I'm going to zoom out here for a second. So this would be delta x, j equals 1 to n, f of a plus j delta x. All right, this is kind of wacky. Just bear with me a little bit. So that easier thing to solve is delta x. So delta x I know is b minus a over n. So it's 4 minus 0. Now, n, I didn't say n rectangles or 6 rectangles. I should say we did say n. So I'm going to leave this as an n. So this simplifies to be 4 over n. So any place there's a delta x, it's a 4 over n. So that's 4 over n. This is a 4 over n. This is still the limit as n approaches infinity. Delta x is fine. Here's my sigma notation. This is f of a. A is where we start, which is 0. Plus j is j. And 4 over n is my delta x. Okay. The limit as n approaches infinity. 4 over n, still in the front, that's okay. Sigma notation, still okay. Now, the 0 plus j, 4 over n, has to get substituted into my function, and my function is x. So when I substitute, this is going to be j 4 over n. You're going to ask me questions here. What happened to the 0? Where did the f go? So just kind of one more time. This quantity, the 0 plus j times 4 over n, gets substituted in for x. But because this is just a linear, very straightforward equation, there's no x squared to put it into. There's no 3 times x to put it into. So this piece right here is the same thing as our f of x. So I know it looks a little weird. Nothing really happened. But it did happen. It's just a boring function to put it into. All right. Now, the only thing that needs to stay inside of the sigma notation is the j. Because these directions tell us that we're only dealing with j. We're not dealing with n. So this 4 over n can pop to the front. Just like derivatives, just like antiderivatives. So the limit as n approaches infinity, 4 over n times 4 over n, j equals 1 to n, and here's j. All right, now we're almost there, I promise. J equals 1 to n times j. Because this is j to the first, I'm going to come back up here to these formulas. J to the first is the same thing as n times n plus 1 over 2. N times n plus 1 over 2. All right, guess what? Now we have an algebra problem that we're going to simplify here a bit. N in the denominator, n in the numerator cancel. This becomes a 2. This is a 1. I promise we're almost there. Limit as n approaches infinity. 8 over n times n plus 1. I think we got everything. Yep, that looks good. Now, the limit as n goes to infinity. Well, it's a limit problem. So if I put infinity in place of n, I have 8 times infinity plus 8 over infinity. It's infinity over infinity. Wait a minute, where have we seen that before? Well, in the beginning, unit 1, sometimes we would factor. And then later on, we learned about L'Hopital. So if I rewrite this as 8n plus 8, you might like it better. Yeah, we can use L'Hopital. So the derivative of the top is 8. The derivative of the bottom is 1. Our little LH, not mathematically accurate, just our little reminder to ourselves. Now there's no place left to put the infinity. So what's the answer? It's 8. Ta-da! Okay, so the geometry, we got 8. With sigma notation, we got 8. Well, this is a bit of a situation. Not all shapes are going to be nice, neat triangles. Bummer. This is awfully cumbersome and clumsy. It will get you to the right answer, but we need something more efficient. And that's where we get into the definite integral. So that's the next lesson. Good job. Let me know if you have questions. Am I going to ask you to replicate this process on the test with all the sigma stuff? No, you have to be able to match this sigma with one of the definite integrals later. And this is kind of what's going on here. So I'll show you about that. So this was just to introduce the idea of rectangles in geometry and sigma notation. Let me know if you have any questions.